physics.
Right, I think I went a wee bit over a score with a big intro on that. For the record, momentum in physics is actual heavy easy, but for some reason Wayne's pure go mental whenever they need to pure work out questions on it. Momentum to a physics pupil in Scotland is the same way as Godzilla was to Tokyo, or Manti to Gyro's Janus with the DSS. There's two reactions that the Japanesers and pupils both have. Run away screaming like a wee Jessie, or stand still, stare at the question, and crap yourself. On the odd occasion or two, you get a pure wee brainy bottom who can do it. Hopefully you's a lot of wee brainy bottoms after watching my momentum video. So what the hell is momentum then? Well, it's a wee bit controversial. Turns out back in the day, some physicists just used to sit about all day pure farting about with physics numbers. One of these bottoms said one day, "Here big chap, see if I pure multiply an object's mass with its velocity, then that's something new, isn't it?" Even figured that in collisions this number stayed the same when we talk about both objects that smack into each other. Now we're in the big time when we say to himself, thing is though, this punter came from Glasgow and his name was Morris Mentum, but his pals called him Big Mo. Big Momentum is about to be physics famous, but all the pure snobs man, pure ganged up and heavy bumped Big Mo out the picture, pure saying, "We can't have a heavy duty bevy merchant for Glasgow pure taking the credit." So all your history books and your textbooks and your wiki-picky internet books don't mention a thing about Morris Mentum. To be fair, Big Isaac Newton did the work already, but Big Mo's name still stuck around, so we call mass times velocity for an object momentum. For some reason we get the wee symbol small p, and the units are kilogram meters a second. Momentum is supposed to be like the power of movement or some crap like that. Cut the button speak. If your mass increases, so does your momentum. If your speed increases, so does your momentum. If you stand dead still with no speed, you've got no momentum. Don't believe me? Chuck a golf ball and a ping pong ball at your pal's head. Tell me which one it goes pure raging over. To pure gaze a wee mental image of what I'm going to pure talk about, go and watch the new A-Team film, which is pure dynamite by the way. There's a bit in it where they're pure falling in a tank with one parachute, and there's this wee mad drone plane thing trying to shoot them down, the kind of things you see in 24 and that. And Hannibal's like to face man, "Here, fire the gun after the side, big man." The wee soldiers flying the drone thing pure serious on their cameras, and they're like, "Is she trying to shoot down our plane?" The bird next to him's like, "No wee man, he's trying to fly a tank." Brilliant man, fly a tank, no danger. If he's fire a shell out a tank to the right when it's pure in free fall, then cause momentum needs to be conserved in that, then the tank will move a bit to the left. Thusly, you fly a tank. To be fair though, you're still dropping down like a brick, but you get the picture. Now for the numbers bit then, you need to heavy remember. First things first, momentum is a vector, which means you need to tell what direction it's pure gone in. For yous lot in school, yous will stick to things going left or right. Everything that moves to right is positive, everything to left is negative. Capiche? Momentum is pure taught about in collisions, and you need to know all three types of them. I'm going to show them this way with a wee snapshot before and after. Unless yous are teenage boys where your alphabet consists of a series of grunts, then yous will use your regular alphabet where U comes before V. So I'll use U for velocity before a collision and V for velocity after it. All yous need to do is work out the total momentum of the objects before a collision. This number is the same as the momentum after the collision as long as nothing pure interferes with it. We call this interfering external forces. I'll be write it as everything before equals everything after and let my maths do the talking. Collision number 1. Two objects pure collide and stick to each other. Work out momentum of both objects added together before using this wee thing here. After the collision, the objects are pure stuck to each other, so use this thing here. You've no 7 of the 8 numbers needed, so you can easily work out the last one. Collision number 2. Two objects pure colliding, separate and go their merry way man. Same as before, work out momentum of both objects before using this and after using this. Collision number 3. An object explodes into 2 bits that pure fire off at different directions and speeds. Before the explosion we write momentum like this, after we write it like this. Simples. Some things to heavy remember though. You must keep your mass in kilograms and you must make your velocity negative if it's gone left and positive if it's gone right. Don't worry wee man if your answer is negative for a velocity, it just means it's gone left. Here's a wee beastie worked example to heavy help you out, man. Physics teachers are crap at drawing, so here we've got two high-tech moving vehicles called trolleys. Trolley 1's 12 kilograms, it's firing along at 10 metres a second to the right. Trolley 2's 10 kilograms and firing along at 8 metres per second to the left. The heavy smack into each other and trolley 2 pure bounces and goes to the right at 10 metres per second. What's the velocity of trolley 1 after colliding, big chap? You need to say to yourself, what type of collision is it? It's number 2, because they separate. Pop down the equations on your paper and fill in the numbers. Now you've only got one missing thing you need to work out. Minus 5 metres a second, wee man, just means it's gone left at 5 metres a second. Just decide what collision it is and fill in the numbers of the right equation. One wee thing though you need to pure remember, and that's about your energy. These things are hefty shifting, so they've got a kinetic energy which is pure e to the k, which equals a half mv squared, isn't it? If you work out this number for the trolleys before and after, then you'll notice a wee difference. You have lost energy somewhere, probably to heat or sound or something like that. This means the collision was inelastic. If your mad energy after your collision was the same as before the collision, then we call that elastic. Nothing really is elastic, but we say wee mad molecules and things that collide in a gas are elastic collisions because it's near enough, you know what I mean? Big balls colliding or car crashes aren't going to be elastic. So there you go then, ya bottins. Away and do your homework without whinging about it being too hard. Catch you Versace.